Okay, this is, we're almost to the end. This is my second last lecture on atomic and nuclear physics. I have three new topics. This PowerPoint goes a little long because I also have some review built in because we have the test coming up next week. But basically, we have three new topics: standard model, radiation, and nuclear reactions. I'm going to talk about all three of them, but then I'm going to have another video after this where I talk about just the standard model. So here I'm just reviewing the different models of the atom back from chemistry. Greek model said that there was a particle that was the smallest piece an element could be. And the Thomson plum pudding model shows us that there's positive and negative charges evenly distributed. Rutherford model has the positive in the center. The Bohr model we talked about last week with the different energy levels. And then the electron cloud model, which is our newest model of the atom. So I'm going to go through some experiments here. These questions do pop up on the Castle Learning that ask you about which experiment was famous for which discovery. This J.J. Thomson experiment is famous for telling us that electrons are definitely negative. And what he did is he fired electrons through this tube, and the electrons were deflected towards the positive plate, away from the negative plate. This meant that the electrons had to be negative. Because the atom is neutral, that meant that the nucleus had to be positive to make the whole atom neutral. Milky and oil drop experiment, I talked about this before. This is where this tells us what the fundamental or elementary charge is on one electron. So we spray some oil into this chamber. The oil picks up electrons just through static electricity. They fall in between a positive and negative plate. Here we're showing red is a positively charged plate, blue is a negatively charged plate, and you can control the potential difference between the two plates and ultimately determine the charge of an electron. Rutherford gold-foiled experiment, again mentioned in chemistry. He fired a bunch of positive charges, basically alpha particles, which I'm going to talk about later in this presentation. Fired these positive particles towards the thin gold foil. The fact that they went through it tells us that the atom is mostly empty space, and the fact that they were deflected tells us that there's this central positive core to the atom. And the Bohr model of the atom, just like the other presentation, each level is associated with a different amount of energy, and electrons absorbed or photons absorbed cause the electron to jump up, and when the electron jumps down, photons are emitted. And again, just like the other lecture, I'm just showing the chart compared to the Bohr model. And also in the other lecture, Compton scattering. So when the photon is absorbed by the atom and the electron jumps up, you can also explain it in terms of collisions. So the incident photon collides with an electron, and then the photon loses energy and the electron gains energy. And a little review here. What is light? Well, light is both particles and waves. How do we know that light is waves? Because when it's in phase, we have constructive interference, and when it's out of phase, we have destructive interference. How do we know that light is particles? That's the photoelectric effect. We shine light onto certain metals, and these metals like to give off electrons when light is shined onto them. And we can measure the energy of the electrons, and we know that light is coming in certain amounts of energy. And those little packets of energy are ultimately photons. And here's just another picture of the photoelectric effect. It's showing the tube. There's the light shining into a charged plate. At the bottom, I have a battery, and the electrons are then attracted away from the positive plate and towards the negative plate. Here's another picture of it that's from a computer simulation. And if you look at the graphs on the right-hand side there, one of them showing the light intensity, that means how bright it is, versus the current. The brighter the light, the stronger the current gets. We need to know that. The bottom one is showing us frequency versus the kinetic energy of the electrons. So frequency, right, as we increase the frequency, we're going closer to blue and violet and ultraviolet and ultimately X-rays and gamma rays. And as I increase that frequency, the electrons have more energy. So here, looking at graphs again for the photoelectric effect. On the left-hand side, as the light frequency gets higher, the electron kinetic energy gets higher, which is what I just said. And if you think about the E equals HF, that means the slope of this line on the left is going to be Planck's constant, H, 6.6 times 10 to the negative 34. On the right-hand side, we have light frequency again, but then we have the electron current. And we see the electron current is perfectly staying the same here because it's not frequency that changed the current, but it was the brightness of the light. So what do we want to remember? The brightness of the light increases the current, and the frequency increases the kinetic energy. So what is light? Just a review here. It's electromagnetic radiation. It's photons. It is affected by gravity. It does have momentum, but it has no mass. In a vacuum, it travels at 3 times 10 to the 8th meters per second, and it travels about the same speed in air. It's a transverse wave, and high energy equals high frequency, which is dangerous. And here's an electromagnetic spectrum. We talked about this in a couple other presentations. And the speed of light, we've talked about this before, right? 3 times 10 to the 8th meters per second slows down in different materials. We have that chart. The old wave formula, V equals F lambda, turns into C is equal to F lambda. And then, of course, E equals HF, and the other way to write it, E is equal to HC over lambda. I'll review from other lectures. Now, this is new, the Standard Model and quarks, and I'm going to have another lecture on this. But real quickly, everything in the world is matter. Our universe is made up of matter. And matter can basically be subdivided into two categories, hadrons and leptons. So leptons, one type of a lepton is an electron. So an electron is a lepton. And the other part of an atom is the protons and neutrons. Protons and neutrons fall on the hadron side of things. And you can see on the left-hand side, hadrons are then subdivided into baryons and mesons, and baryons are comprised of 3 quarks, and mesons are comprised of a quark and an antiquark. So what are quarks? And briefly I'm going to talk about it now, and then I'll talk about it again later in the week. Quarks are what make up protons and neutrons. So on the left here, if you have a proton, you can think of it as 3 quarks being inside of it. And on the right, I have a neutron. You can think of that as being 3 different quarks inside of it. So quarks really don't exist in nature by themselves. They usually pair up or make groups of 3. When they make groups of 3, they can make protons and neutrons. And if you look at the difference between the proton and the proton has 2 of the gold and 1 of the gray, and the neutron has 2 of the gray and 1 of the gold. So they're very similar. So if the gold, which is the U, we call that the up quark. If a U turns into a D, then I would have 2 Ds in a single U, so a proton would turn into a neutron. So again, in a future lecture, but an up quark turns into a down quark, and a proton becomes a neutron. Notice the U on the left can turn into a D on the right, and then a proton would be a neutron. So just a little more information on the Standard Model here, this new graphic towards the top. I included this not because you need to know bosons or the Higgs boson or anything like that, but it's showing us that protons and neutrons are baryons and baryons are hadrons. And it's also showing us that electrons fall under the leptons. So what do we need to remember? Protons and neutrons are made of 3 quarks, and those 3 quarks are baryons, which are hadrons. Electrons, on the other hand, are leptons. So if you look at the graphic all the way to the right, at the top, it has these different types of quarks. These are their names: up, charm, top, down, strange, bottom. And I have their charges written there too. So they have a charge that's less than 1 elementary charge. An up quark, for example, has a charge of positive 2/3 e. A down quark, on the other hand, has a charge of negative 1/3 e. And then I have the leptons. Notice that an electron is a lepton. So here I'm showing how protons and neutrons get their charges. Protons and neutrons are both made up of 3 quarks. So a proton, as we know, has a +1 or +1 e charge. Where does that come from? Well, the picture is showing us a proton is a up, and a down. So up is +2/3. Another up is again +2/3. A down is negative 1/3. So if I add +2/3, +2/3, and negative 1/3, I get positive 3/3 or +1. So up, down is +1. That's a proton. Neutrons, on the other hand, I have to have a down, down, and an up. So I have negative 1/3 down, negative 1/3 down, +2/3, which is the up, and those added together come out to be 0 or neutral. So I said our universe is made up of matter, but there's also this stuff called antimatter. Antimatter is the opposite component of matter. When a particle of matter is created, antimatter is also created. Antimatter has all the same characteristics as matter, but always has the opposite charge. So if an electron is matter, the anti-electron, which we call a positron, is the exact same thing, but it has a positive charge. And a proton normally has a positive charge, so an antiproton has a negative charge. So the picture to the right, we have hydrogen, has an electron and a proton, and antihydrogen has a positron and an antiproton. Now the reason antimatter is very difficult to find in our universe is because when antimatter and matter come together, they annihilate, which means they explode and they turn into pure energy. So here's a picture of how matter is created. On the left, we have 2 gamma rays coming together. There's an explosion, and it creates an electron and the anti-electron called a positron. The picture to the right is showing how we can do this in the laboratory. This is a cloud chamber, and when the gamma rays come together, or when we make matter in other ways, because I think this picture is actually showing a gamma ray hitting an atom, but when we make the matter, it creates the electron and the positron, and that's those curls there, because this cloud chamber is inside a magnetic field, and when a charged particle is in a magnetic field, it travels in a circle. And because the spirals are in opposite directions, it means the 2 particles, the electron and the positron, have opposite charges. And this is another picture of matter being created. A photon comes in, slams into this atom, and at the bottom, you can see that an electron is created. This graphic is calling it a negatron, but that's just another name for an electron. And then the upward facing arrow is the positron. And you know, and if this is taking place on Earth, where there's air and all kinds of objects, there's a lot of free electrons around. So the positron immediately finds a free electron and annihilates and turns back into energy again. So here's another picture of it: an electron and a positron. They will naturally come together. They will annihilate and give off photons. And when that happens, we can use the formula E is equal to mc squared. So if I asked how much energy is given off when an electron and a positron annihilate, you take this formula. You take the mass of an electron and times 2, because it's the mass of an electron and the mass of a positron, multiplied by the speed of light squared, and that's how much energy you get in joules. So just a little bit of chemistry review here. If I have some sort of atom, here it's represented as the symbol X. This would be the chemical symbol for the element. And then I have A and Z, the atomic number and the atomic mass. If it's hydrogen, since it has only one particle in the nucleus normally, it's just H1 over 1. And an electron isn't an atom, but we can also represent it as 0, -1. So a little review from chemistry of isotopes. Remember, the number of protons is what makes an element that element. So hydrogen has 1 proton, but this is 3 different versions of hydrogen. They all have 1 proton, but the isotope in the middle also has 1 neutron, and the isotope to the right has 2 neutrons. So there's something called the strong nuclear force. The strong nuclear force is what holds the nucleus together. It holds all the particles together, protons to protons, neutrons to neutrons, and protons and neutrons to each other. What we need to know here is it's very strong, but it only works for very short distances. Binding energy is the energy needed to break apart the nucleus. So when we talk about radiation or we talk about nuclear fission, we're talking about the nucleus coming apart. So in the other lecture, I talked about E equals mc squared, and I talked about E is equal to delta mc squared. So what we're saying is, if I have a nucleus breaking into 2 smaller atoms, if I were to add the weight of the smaller atoms and compare it to the weight of the original atom, there's a difference in mass. That's how much energy there is in the binding energy. So on to radioactivity. There's 3 types of radioactivity, as you might remember from chemistry: alpha, beta, and gamma. Alpha has alpha particles, which is basically a helium nucleus. Beta has beta particles, which is basically an electron. And gamma particles are electromagnetic waves like light, except higher frequency, so their particle is the photon. So off to the right, I have a graphic. I'm showing that alpha can be stopped by paper. It's the weakest. Beta is being stopped by metal. And then gamma rays have to be stopped by like really thick concrete. And even then, some of them are going to get through. So gamma is the highest energy. And then to the left, I have this handwritten notes here. Alpha, beta, gamma. Alpha, I'm showing it's a helium nucleus, so 4 over 2. Beta, I'm showing it's an electron, so it has a charge of -1. And then for gamma rays, I just wrote photons. So here's a graphic, again, reviewing the same thing: alpha, beta, and gamma. Notice that alpha has a daughter, beta has a daughter, but in gamma, I just go from an unstable element to a stable element. It also has well, I guess it's also being called a daughter, but we're going to find out in the next slide that it's actually the same element again. So again, the strong nuclear force, we must overcome this strong nuclear force for radiation, because we have to break this force for the nucleus to lose particles. So again, just reviewing alpha decay, one of the worksheets is going to talk about alpha decay. So this has an element with 88 protons, and then it falls down to 86. So it gave off 2 protons, and it lost 4 particles total. So this is how we know that it's alpha. Also, we know it's alpha because here we can just see that there's a helium nucleus being given off. So the element loses 2 protons and 4 particles total. And then I'm just showing that again to notice that the number of protons is decreased by 2. In beta decay, a neutron turns into a proton, like I was talking about a few slides earlier, and a beta particle, an electron, is released. This is caused by the weak force. So if you look at the in the middle here, there's this blue neutron, and you can see it's turning into the goldish proton here, and then it also gives off an electron, and it gives off a new particle I haven't talked about yet. This is called an antineutrino. So my handwritten example here, I have this thorium-234 thorium-90 turns into 234 Pa, whatever Pa is, 91. So the 234 stayed the same because a neutron turned into a proton. So the number of particles in the nucleus stayed the same. But the 90 goes up to 91 because I have a new proton in the nucleus. So the graphic to the bottom right here shows that if I have some element X and the number of protons is Z, then the daughter Y is going to have protons Z plus 1, one more, plus a beta particle, plus the small particle called antineutrino. Antineutrinos travel very fast, close to the speed of light, but not the speed of light, and the mass is very small, not 0, but incredibly, incredibly small. So here's another example of beta decay. So how do we know it's beta decay? Well, one way we know that is we can just see the particle being given off as an electron. But even if we didn't know that, it started out with 3 protons, it goes up to 4. So this has to be beta. There is a positive version of beta decay. I'm not going to explain it in detail. Just normal beta decay gives off a negative electron, and positive beta decay actually gives off a positron, or a positive particle. And then we have the third type, which is gamma decay. Now, the A is just a symbol being used to represent some element. The asterisk means it's unstable. So A unstable eventually turns into A stable. And it does this by giving off gamma radiation in the form of photons. So in the middle, that backwards Y looking thing, that's just another way of writing the Greek letter gamma. So here's an example with the chemistry at the bottom. We have 23491, and that turns into 23491. Well, nothing changed. Yeah, nothing changed. Same number of protons, same number of neutrons, but it's giving off gamma rays. So here's just a review of all 3 of them together. Alpha, you lose 2 protons. Beta, you gain a proton. And gamma, proton stays the same. And again, more examples here like you'll have to do for the homework. The top one goes from 92 to 90, so it's got to be beta. Then the next one, the same element, uranium-235, goes from 92 to 93. It's gaining 1, so that must be beta. And then the last one, 92, stays 92, so that must be gamma. Half-life. So real quickly, you should remember this from chemistry, but this is how long it takes for half of the element to be given off as radiation. So if some object has, well, here it's saying 1 half-life equals 5,730 years. So on the bottom, 1, 2, 3, 4 isn't years, that's half-lives. So from 0 to 1, we're going to go from 10 grams to 5. Then the same thing, another 5,730 years, we're going to have half of that, 2.5 grams. And then another 5,730 years, and we're going to have 1.25, and so on. Each time I have half of what I started with. Now, carbon-14 is important because we use it for carbon dating, and that's to date things that used to be alive. So real quickly, there's a certain amount of carbon in the air, and the certain amount of that carbon in the air is radioactive, and we know what these percentages are. And so that carbon in the air becomes the plants around us, right? Plants take in CO2, and then plants get eaten by animals, and animals get eaten by other animals, and so on. So if you have something that used to be alive, a plant or an animal, you can look at how much carbon 14 it has now, the ratio of carbon to carbon 14 now in 2020, and we know what that ratio was when it started, right? Because all things have that same ratio. So we look at the difference between the two, and we can do the math backwards, and we can tell how old something is. And now the last topic is nuclear fission and nuclear fusion. Nuclear fission, I want you to remember, fission is breaking apart. This is how atom bombs work. This is how nuclear reactors work. We take a large nucleus, we fire a neutron into it, and that large nucleus breaks into two smaller nucleuses. When it does that, it releases a huge amount of energy. That's nuclear fission breaking up. Nuclear fusion, on the other hand, is coming together. Nuclear fusion is what happens in the sun. Nuclear fusion is what happens in not atomic bombs, but nuclear bombs. We do not use fusion in nuclear reactors because it takes incredibly high temperatures for fusion to occur. And other than weapons, we can't create those super hot conditions for it to happen. But basically, what happens is hydrogen comes together. So you can see yellow represents a proton. So deuterium and tritium are two isotopes of hydrogen, but they're both hydrogen because they both have one proton. So they come together and they create helium. So you can see that helium has the two orange pluses, the two orange protons coming off. So hydrogen comes together and makes helium. This is nuclear fusion, which happens inside of stars. Okay, so I think this is the last slide here. So I want you to do the worksheets that I have up on the website. I think I'm going to have some other videos up there as well. I'm going to have a help video where I'm doing some of the problems with you like I usually do. And then later in the week, I'm going to talk a little bit more about the standard model, and then probably quiz on Friday. And then, like I said, I'm going to have a test next week. It's not the final exam, it's just the end of unit test that everybody needs to take. And then that'll finish up your grade for the fourth quarter.